Imagine we have a square that has a side length of 1. First, we're going to find the measure of this angle right over here. We know that squares have corner angles that measure 90 degrees each. And we know that since squares have rhombus properties, the diagonals bisect the angles. So that means this 90-degree angle is being split in half into two equal parts, as well as this 90-degree angle over here. Now, we're going to find the length of the diagonal BD. Notice that we have two right triangles over here, each with legs that are a length of 1. So if I want to find the missing side, the hypotenuse, I can use the Pythagorean theorem to do that. A squared plus b squared is equal to c squared. Plug in 1 for the legs, and I'm solving for the diagonal, which is the hypotenuse. And I get that c is equal to radical 2. What we have here is our first kind of special right triangle, the 45, 45, 90 triangle. And as you can see here, the sides are in the ratio 1 to 1 to radical 2. The 1 to 1 part of the ratio means that two of the sides, which are the legs, have the same length as each other. Remember, when a triangle has two equal sides, it also has two equal angles. So if we have a 45, 45, 90 triangle, the sides opposite those 45-degree angles are going to be equal to each other. The hypotenuse of the 45, 45, 90 triangle is radical 2 times as large as the legs. Over here, I have an equilateral triangle, and we know that equilateral triangles have angles that measure 60 degrees, because remember, 3 equal sides, 3 equal angles. And when we have an equilateral triangle, the altitude does something very special. It also bisects the angle. Once again, that's only because it's an equilateral triangle. It's something special that happens in an equilateral triangle. So each of these angles up here is 30 degrees. Now we're going to find the measurement of BD, of altitude BD. And what we have here are two right triangles. And in these two right triangles, we already have the hypotenuse. Remember, the hypotenuse is across from the 90-degree angle. So the hypotenuse is 2. And we have one of the legs. Each of these legs is length 1. Once again, that's because this is an equilateral triangle. So the altitude does something really special. It not only bisects the angle, but it also bisects the side. So using the Pythagorean theorem, which is a squared plus b squared equals to c squared, I have 1 squared plus b squared is equal to the hypotenuse squared. So what I have here is 1 plus b squared is equal to 4. Subtracting 1 on both sides, b squared is equal to 3, so b is equal to radical 3. What we have here is our second kind of special right triangle, the 30, 60, 90 triangle. And the 30, 60, 90 special right triangle has sides that are in the ratio 1 to radical 3 to 2. What this ratio means is that the smallest side, which is across from the smallest angle, across from the 30-degree angle, is half the length of the biggest side, which is across from the 90-degree angle, the hypotenuse. The middle biggest side, which is across from the middle biggest angle, the 60-degree angle, is radical 3 times as large as the smallest side. Over here, we're going to practice using the ratios for the special right triangles. So in the first example over here, I have a triangle with a 90-degree angle and a 60-degree angle. And if I add 90 and 60 and subtract from 180, because all three angles of any triangle make 180 degrees, I have that this is 30 degrees over here. So I have a 30, 60, 90 special right triangle. And as we saw in the previous slide, the ratio of the sides of 30, 60, 90 triangles are in the ratio 1 to radical 3 to 2. So all I have to do is determine which side I'm finding, which side I already have information about, and if I'm going bigger or smaller. If I'm going to go bigger, I'm going to multiply according to the ratio. If I'm going to go smaller to a smaller side, I'm going to divide according to the ratio. So let's start with finding y first. Actually, let's find x first. So I already have the smallest side across from the smallest angle. So I already have the smallest part of the ratio. The one part of the ratio is 8. Now I'm going to a bigger side. I'm going to the middle biggest side because it's across from the middle biggest angle. The 60-degree angle is in between. Not as big as the 90, but bigger than the 30. It's the middle biggest angle. So the ratio tells me that to go from the smallest side to the middle biggest side, I'm going to multiply by radical 3. So I'm going to take my 8 and I'm going to multiply it by radical 3. 8 times radical 3 is 8 radical 3. So the measurement of the side over here, the middle biggest side, is 8 radical 3. Now we're going to find y. And y is the largest side across from the 90-degree angle, the hypotenuse. According to the ratio, the relationship between the smallest side and the biggest side is 1 to 2. So that means to get the biggest side, I'm going to take the smallest side, which was 8, and I'm going to double it. And I get 16. Moving on to the next example over here, we have a 45, 45, 90 triangle. The 45, 45, 90 triangle has the ratio 1 to 1 to radical 2. Two of the sides are the same length. The hypotenuse is radical 2 times as large as the legs. What I have here is one of the legs because it's across from one of the 45-degree angles. And what I need to find is the hypotenuse. According to the ratio 1 to radical 2, if I'm going from one of the legs to the hypotenuse, I'm going bigger, so I'm going to be multiplying, and I'm going to multiply by radical 2. So 8 times radical 2 is 8 radical 2. Moving on to the next example, I once again have a 30, 60, 90 triangle, just like example number 1. And this time, the side that they give me information about is the middle biggest side. It's across from the middle biggest angle. So what we have here is the radical 3 part of the ratio. So what we're going to do first is we're going to find the smallest side. We're going to find x, which is the smallest side because it's across from the 30-degree angle. And once we have the smallest side, it'll make it really easy for us to find the biggest side because then we can just double the smallest side. So in order to get from the middle biggest side, which is what we have, to the smallest side, we're going smaller. So we're going to be dividing. And the ratio says that we're going to divide by radical 3. So I'm going to take the middle biggest side that we have, 12, and I'm going to divide it by radical 3. But unfortunately, we can't leave our fraction like this because we can't have a radical in the denominator. It's not simplest form. So what we have to do now is we have to rationalize the denominator. That means we have to get rid of the radical from being in the denominator. So what we're going to do is we're just going to multiply the top and the bottom of the fraction by the radical that we want to get rid of from the denominator. So top and bottom by radical 3. What I have over here is 12 radical 3. Radical 3 times radical 3 is radical 9, which is just 3. And then finally, 12 divided by 3 does simplify. That is 4 radical 3. And that is our smallest side. Now that we have the smallest side, to get to the biggest side, all we need to do is take the smallest side and double it because the smallest side and the biggest side are in a 1 to 2 ratio. So all I need to do is take 4 radical 3 and multiply it by 2 to get the biggest side. And that would be 8 radical 3 for the biggest side. Finally, over here, we don't have these two angle measurements, but I know that these two sides are equal. So that means the angles opposite those sides also have to be equal. So if we take 180 and we subtract the 90-degree angle that we already have, we get 90. And then if we divide by 2, these have to be 45-degree angles. So what we have here is a 45, 45, 90 triangle. And what I have here is the biggest side across from the biggest angle. So in the ratio, I have the radical 2 part of the ratio. So I'm going smaller and I'm trying to find what the legs are. So I'm going to be dividing because I'm going smaller. And the ratio tells me that I'm going to be dividing by radical 2. So I'm going to take the biggest side, which is 18, the side that I have, and I'm going to divide it by radical 2. But once again, we can't have a radical in the denominator, so we're going to rationalize it. We're going to multiply the top and the bottom by the radical that we want to get rid of. So in the numerator, we now have 18 radical 2. 18 times radical 2 is 18 radical 2. And radical 2 times radical 2 is radical 4. Radical 4 simplifies to 2. 18 over 2 is 9. So we have 9 radical 2 for the length of each of the legs of this 45, 45, 90 triangle. We're going to do a couple more examples. This one over here says find the measure of the diagonal of a square with a side of 3 meters. So I'm going to draw a square. Here's my square. And the sides of my square are given as being 3 meters. And I need to find the diagonal. So in a square, we know that there are 90-degree angles in the corners. And we know that the diagonal of a square bisects the angle because a square also has the properties of rhombuses. So these are all 45-degree angles. So what we have here are two 45, 45, 90 triangles. And we need to find the biggest side, the side opposite from the 90-degree angle. So we already have the legs, which are 3. So to get from the legs to the hypotenuse, we're just going to multiply by radical 2. So the length of the diagonal is 3 radical 2. Now we're going to do the next part of the question. So I'm going to erase this. In the next part, the question's a little different because this time the diagonal has a length of 3, and we need to find the measurement of the side of the square. So this time, in our 45, 45, 90 triangles, we now have the hypotenuse, and we actually need to find the legs. So we have the radical 2 part of the ratio. So to get the legs, we're going smaller, so we're going to be dividing. And the ratio tells us to divide by radical 2. So I'm going to take the hypotenuse that we have, and I'm going to divide by radical 2. And we are going to need to rationalize the denominator. We can't leave a radical in the denominator. So we have 3 times radical 2, which is 3 radical 2. Radical 2 times radical 2 is radical 4, which simplifies to 2. 3 doesn't divide into 2 evenly, so we can just leave it as 3 radical 2 over 2. And that's the measure of one side of the square. In fact, it's the measurement of all the sides of the square because a square has 4 equal sides. Moving on to another example, this time we have a rectangle. And the shorter side of this rectangle is 2 inches. The diagonal of the rectangle is double the shorter side. So if the shorter side is 2 and the diagonals double it, that means that's going to be 4. Find the perimeter and area of the rectangle. So a rectangle, just like a square, has 4 corner 90-degree angles. But unlike a square, the diagonal of a rectangle does not bisect the angles because a rectangle does not have rhombus properties. So I can't say that these two angles are 45 degrees. So I don't know if I have 45, 45, 90 triangles here. I also don't know if I have 30, 60, 90 triangles here. So as far as I know, I don't have any special right triangles. But I do have regular right triangles. So I can use the Pythagorean theorem to find the other side. So I'm going to plug into a squared plus b squared equals c squared. The hypotenuse is 4. One of the legs is 2. And we're finding the other leg. So we have b squared is equal to 12. So b is equal to radical 12. And if we wanted to write that in simplest radical form, we can break that up into radical 4 and radical 3. Radical 4 is 2, so that would be 2 radical 3. So the perimeter would be 2 radical 3 plus 2 radical 3 plus 2 plus 2. So that would be 4 plus 4 radical 3. And the area would be length times width. So that would be 2 radical 3 times 2, which would be 4 radical 3. We're going to take a look at this next question. It says find the length of the altitude drawn to the hypotenuse of a 30, 60, 90 triangle if the short leg is 2. So we're talking about a 30, 60, 90 triangle here. So let me make one. It doesn't matter which one I make the 30 and which one I make the 60. But if I made the 30 here, then that's going to be the shorter side. And if I made the 60 here, then that side's going to be longer. And this is the hypotenuse. And it says that we have the altitude drawn to its hypotenuse. So here's the altitude drawn to its hypotenuse. And an altitude creates 90-degree angles. So what I see here is that we have a right triangle altitude theorem situation. We have a big right triangle with an altitude drawn to its hypotenuse, creating two smaller right triangles. So we could also potentially here use the leg rule or the altitude rule if we need to. The short leg is also 2, so I'm going to put in 2 for the short leg of the 30, 60, 90 triangle. Once again, I knew this was the short leg because it is across from the 30-degree angle. We need to find the length of the altitude. So I could use the altitude rule, but in order to use the altitude rule, I do need to have the two segments of the hypotenuse. What I do have is a 30, 60, 90 triangle. So I could use my ratio 1 to radical 3 to 2 to get more information about the other sides of this triangle. So the 2 is the short side across from the 30-degree angle. So the middle biggest side across from the 60-degree angle would be the shorter side times radical 3. So that side would be 2 radical 3. And this whole hypotenuse, which is the longest side of the 30, 60, 90 triangle, would be the short side times 2. So that would be 4. Now I still don't have the information that I need for the for the altitude rule, because for the altitude rule, I need the two segments of the hypotenuse. But what I could use is the leg rule first, and I can use the leg rule to figure out what one of the segments of the hypotenuse is. And then if I find what this segment is, and I know the whole hypotenuse is 4, I can subtract this from 4, get this, and then use the altitude rule. So that's what I'm going to do. The leg rule is the hypotenuse over one of the legs, whichever one you're focusing on. I'm going to pick the 2 because 2 is nicer to work with than 2 radical 3. Over the part of the hypotenuse, the segment of the hypotenuse that's directly below it. So I don't know that. So that's going to be x in this situation. Cross multiply. I have 4x is equal to 4. And that means x is equal to 1. So that means over here, this segment of the hypotenuse is 1. And 4 minus 1 is 3. So now I have both segments of the hypotenuse. And now I can use the altitude rule because I have both of the segments, so I can plug them in now, 3 and 1. And I'm looking for the altitude. That was my goal, to find the altitude. 3 times 1 is 3. X times x is x squared. Square rooting both sides, we have x is equal to radical 3. So the length of the altitude is radical 3.